To start. Thank you. Your Excellency, Ambassador of Switzerland, Cyprus, and dear colleagues, you have also, we are also waiting in a while for the President of the Cyprus Institute to arrive, but we should not delay because we also have online audience. Welcome to this week's and this month's first colloquium, because we will have at least another one towards the end of the month. And we are very happy to host Professor Margarita Chli, who has recently been appointed at the University of Cyprus, but she has also a professorship at ETH, the world-famous technical university in Zurich in Switzerland. So she has recently been awarded an ERC Consolidator grant, and she will build her research team at the University of Cyprus. And well, her specialization is robotic vision. So she is a professor of robotic vision and director of the Vision for Robotics Lab at both Cyprus, the University of Cyprus, and ETH. And she has, as you imagine, she has given several talks, not only in academic conferences and outlets, of course, but also at the World Economic Forum in Davos. And we are very much looking forward to her talk. So, Mrs. Chli, thank you very much.
Thank you very much for the kind introduction, and thanks for the invitation. It's really a pleasure to be here, and I'm humbled by your presence. Let me start my timer. So yes, this is about vision-based robotic perception. So to put it simply, we're trying to teach robots to see. The question is, are we there yet? So I wanted to show you this video here. So here is a cyclist, and you can see the view from a drone that is following the cyclist. There's like 6 pairs of images that are looking at the scene. And this drone is a Skydio drone. You can buy off the shelf today, and it can follow you while you're doing your favorite sport. So you can see that, for example, you can do cycling, you can do skiing, and you can buy this nice small toy to follow you around while you're doing your favorite thing. So the question is, if we do have off-the-shelf systems like this, is there any more research to do in the area? Well, you might say, it's the second slide, we're not going to go home yet. So still, there's a lot more to do, and I wanted to blow your mind a little bit by showing you where we want to go with this. So think about nature. What examples do we have of visual perception and visual understanding in nature? So look at this eagle. It's planning its path such that it's able to grasp the fish while they're both in motion. And it's able to do that by spotting the fish through water. And for whoever has worked with vision knows that water, specularities, and things that move around is very difficult to work with vision. So this is a perfect example where control, manipulation, visual perception, everything comes together in something like this. Then, so how nice would it be if we had drones that they are able to do something like this? Or even more so, my second screen doesn't work, but okay, so we need a little bit of zen until that happens. So you can see now this flock of birds, they're flying in seemingly perfect unison, creating these beautiful formations. Maybe they're crashing into each other, I don't know, but they seem to be recovering well. So how could a swarm of drones be navigating in the space around us in such a seamless, effortless way? So I have taken now all of these problems, and I have broken these down into 3 distinct challenges that we are aiming to address in order to enable things like this, okay? So the big question is, how can we equip our robots with skills? What is the sufficient level of skills that we need to equip them to be able to achieve things like this? So first of all, we need high-fidelity SLAM. SLAM, I'm going to go into it, but it's about estimating where you are and estimating what the space around you looks like. So ego motion and scene estimation. Then on top of that, you need some rich scene representations in order to be able to reach out to grasp an object or to do actually path planning, to move from A to B. And then once you have agents able to deal with challenges 1 and 2, then it would be lovely if we could have them collaborating to do something useful when they're employed to do something, a common task together. So as I said, I've broken this big problem into 3 distinct challenges. It's a pretty naive distinction, okay? But this would also be the index in the talk. I'm going to go through these challenges. I'm going to explain a little bit what they are and give you some ideas, some idea about the works that we have done in the lab to be able to address them, okay? By no means is any problem solved, otherwise I wouldn't be calling myself a researcher. We have approaches for different problems, okay? So let's start with challenge number 1, high fidelity SLAM. Just out of interest to see the kind of audience I'm looking at, has anyone, or do you guys know what SLAM is? No, okay, good. So SLAM is nothing to do with tennis. It stands for simultaneous localization and mapping, and it does exactly what the words say, okay? So the idea is that you want to address this question: how can I track the motion of a robot, or a camera if you like, while it is moving in an unknown environment using onboard sensors? So how do we do that? Well, take a look at this video here. As humans, we're pretty good at understanding how the camera has been moving in order to capture a video like this. So you can already imagine how the camera has been moving. Maybe you can even see the person walking. So we make more high-level assumptions and deductions from what it is that we see. So the question is, how can we make the system, a robot that is carrying this camera, how can we make it understand, estimate this motion, okay? So how do we do it? Well, in traditional SLAM, we pick up some natural scene features like the square patches that you're looking at here. We judge how these move from one frame to the next, and then we start reasoning about how the camera has been moving in order to capture this motion. And on the right-hand side, you can see the kind of map that is being built, or the kind of trajectory. This is now ancient history. That's why the video is old. But it's a good depiction of what traditional SLAM systems are doing nowadays. Right, fast forward a few years later down the line, we put a downward-looking camera on a drone that's like this big, and we showed for the first time that it is possible to automate the flight of such a small aircraft using vision-based cues only, okay? So we are in a firefighter's training area. You can see in a second, again, the kind of map that is being built is very different than what humans use to navigate, right? So this is where the camera thinks is, this is what the environment thinks, looks like. So it's only picking out these features from the environment and trying to see them from different viewpoints to estimate their 3D location. And these are enough for the robot to understand where it is. Now, I have to tell you that for a video like this to happen, we had to go on site 2 days in advance to tune our cameras, to tune our network reception, to make sure that, well, the gain in the cameras is properly calibrated with respect to the lighting of the situation. So, yes, we did SLAM, but was it high fidelity? Well, not really. Not really, and that's why we have been working towards it ever since. So I'll give you some examples on the problems that we have. So here is Bahnhofstrasse in Zurich. So this is something like Margarita pedestrian street. And my student is walking, holding this sensor head, walking down one side of the street and coming back up the other. Okay, so you can see the trajectory plotted here in red. Features are being estimated, and they're being used to estimate the trajectory. So this is a straight street. So basically, what happens is that these 2 locations should correspond to the same place. So what has happened in the meantime is that we have accumulated a lot of drift. So no matter what kind of SLAM system you use, even if it's the best system in the world, if you are not using global information, global sensing data, you're bound to drift. So good SLAM systems drift slowly, but drift is inevitable. So what happens in cases like this? We need to make sure that there is a thread running in the background that is asking, the robot is asking itself, have I been to this place before? Then moves to the next one. Have I been to this place before? So this is what we call place recognition, to re-recognize a place that you have been to before during your trajectory. And the way that we do this is in a very similar way with how Google Images is working. So we query the current view with respect to the rest of the experiences of the robot from this trajectory, from previous trajectories, or whatnot. So on this process of this problem of trying to identify whether we are returning back to a location that we have been to before, we have different problems. So different places can appear to look the same. The same place can appear to look very different, or even more different, when you think about seasons and time of day. Okay, between day and night. And on top of that, when you're experiencing the scene with a drone, as if this was not enough, you also have the problem of viewpoints. So for humans, it's very easy to understand that these locations correspond to each other. Maybe these locations that correspond to each other, maybe that's a little bit harder. But the rest, you are trained to be able to recognize what makes a place distinctive and what not, okay? So let's talk a little bit about the viewpoint changes here. So yes, we can see that that's more or less the same place. How can we make the drone understand that, yes, this is the same location? So one of the ways that we are working with is geometric vision. So trying to run, as SLAM is running on the background and we are estimating a sparse map of the environment, we are looking at how we can densify this map to be able to deal with big changes in viewpoint from 0 to 45 degrees, to up to 45 degrees. And the change in the visual feed that you get is so different that traditional systems, they fail. So here we use both dense depth map cues as well as geometry from the scene that comes from sparse scenery to be able to match the current trajectory, the blue, back to the red reference trajectory. Now, what happens when you're dealing with different seasons and different illumination changes? And you can look at these examples here. These are results out of a system that has been trained, a convolutional neural network. So this is purely learning-based. It's a system that has been trained using webcam images of different places coming out of June and February. So we have examples of the same place coming from summer and from winter. So the system has learned to be able to compress all that information that is not really distinguishing one place or not. So for example, snow is something that should be suppressed as information, although it occupies a lot of our pixels, right? So it should be suppressed, and the system learns how to do that in order to be able to say, this place is actually the same as this one that I have seen back in whatever, June, okay? And it also learns what makes a place distinctive to not be confused with other places that have been experienced in the trajectory. Now, I have to tell you, though, that the trick here is that all these images are upright. The moment you tilt a little bit your camera, you roll it basically, then this does not work any longer because it hasn't been trained with images that are tilted. It has been trained on upright images. So there is a beauty to learning techniques, but you have to know the limitations that come from your data sets. Right, so apart from algorithmic perspectives, we've also been working with different sensors that then open doors to other algorithmic challenges. So event-based cameras. Has anyone heard of event-based cameras here? No. Event-based cameras are cameras, they look like this, and they capture changes in intensity, okay? They don't capture intensities. So you wouldn't get a black and white image. We just show it there for understanding. So every pixel has an individual sensor, and every such sensor, every such pixel fires when there is a change from dark to light, from light to dark. Okay? So what it captures is these changes in intensity. But the beautiful thing of these cameras is that we no longer have this notion of frames. Okay? So every pixel can fire at its own time. So you can have completely asynchronous things happening, right? And that's opening a whole lot of challenges because we don't have to sync, well, I will go that in a little bit, why this is important. So we need to think of time as a continuum instead of discrete that traditional SLAM systems are doing. So what comes for free is that such cameras can look in the dark in places where traditional vision systems would fail, okay? But the trick is to be able to identify which of these events are corresponding to stable landmarks to be able to track to do my SLAM. And also, so that enables tracking in dark scenes, but also at high speeds. So when you have your camera mounted on your drone and your drone is flipping, then if you can imagine the kind of images you would get from a flipping drone, they would either be very blurry or blurry and start-stoppy. So there's a lot you're missing in between the camera frames when there is a fast motion, okay? So such cameras are giving us an insight, so you can look at these colorful events that they precede the intensity image. You can see that's 10 times slower than real time. So these cameras are giving us an insight into what happens in between those camera frames. So, right, we have different sensors. How can we fuse all these sensing cues? Top-performing SLAM systems, they usually have a discrete set of motion estimates. So they estimate motion. So if this is your ground truth, this is how your camera really moved, this is how your robot really moved. With a discrete set of motion estimates, you're estimating your motion here, 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 or every now and again, basically, usually drawn out of visual and inertial cues, for example, for drone navigation. So obviously, the problem here is this approximation that we're making, that we don't really know about what happens in the camera or in the robot in between these motion estimates. So this really comes to fuse together with what I said before about event cameras. So, so there's undetermined motion in between the discrete estimates, and also sensor syncing becomes very important. So there's a lot of sensors out there that you buy them with a high price because they're hardware synchronized. Now, what we are working towards, and also the community is working towards, is continuous time SLAM. So instead of assuming a set of discrete estimates, we are parameterizing our trajectory using splines, B-splines in this case, that my student decided to call this system HyperSLAM. So there's the code here in case you want to try it out yourself. So it's still an approximation to the ground truth trajectory, but the key thing here is that we have an estimate about where the camera is at each moment in time, okay? And we subject this to nonlinear least squares optimization, and using a sliding window inside which we're optimizing, we are able to keep this running real time. So what comes for free is this support for asynchronous sensing, like event cameras, for example. So we tried the visual inertial, stereo inertial version of this system compared against some of the most high-performing SLAM systems out there. And HyperSLAM performs comparably to the state of the art, but where the killer application is when there is frame dropping. When there is frame dropping, all these systems are not designed to work well, so obviously they would fail. But in such cases, the continuity in time would help you, or does help you, have better estimates in what happens in between your camera frames that are being dropped. And just a small addition for those of you who can follow up to this point, just to go a little bit deeper. Some of the one problem that I'm really excited about is, what if, this is my trajectory with a spline basis here, and I usually try and optimize over all of the spline bases. So what if I can be selective on which parts of the trajectory to optimize? So what if I could access which spline bases to modify based on how uncertain I think they are? So having covariance estimates. So one thing that we are working towards is Gaussian belief propagation for distributed continuous time SLAM. That is, I think, is a good key for decentralized SLAM and decentralized updates, and the covariance estimation comes for free. So for high fidelity SLAM, zooming out, challenge number one, we've been experimenting with different sensors, with deep learning, with place recognition. We've taken all guns out and trying to fire at the problem from different perspectives. Why? Because we want to give our robots a sense of space. Where is the robot? What is its pose? And what is the map around it? And the key word so far is that this map has been largely sparse, which brings me to the second challenge of what it is that we're trying to do. So we're trying to build richer, denser scene representations. Why? Because with a point cloud, you're not able to confidently reach out your manipulator arm and make sure that there's free space in between your points, or whether I'm going to crash into an obstacle. Or for path planning, where actually autonomy comes into play. And here you can see an example. There's a drone that is taking off, and it's using a single camera, is looking sideways this time, and using this single camera and some depth estimates that come from both SLAM and a learning technique. It's estimating this grayscale dense map that you're looking at here. This grayscale map, we compare against a laser point cloud that is taken, you can see it in red. So this is taken using a Leica tripod that we've placed in different locations inside this yard, and went away back in the lab and registered all these point clouds together to formulate the best thing that we could gather as a ground truth data. So you can see that the intensity, the vision reconstruction, vision-based reconstruction is not perfect, especially when you see these windows, right? So when we pull the reconstruction down, you can see various things happening in the windows, right? Because specularities are not a good thing for vision. So these, the shiny surfaces are not really helping us. But it is maps like these, such dense maps, that are helping us do some autonomy. So here there's that drone. It takes off and it knows nothing about the scene. There's a pilot that is following that drone just for safety. So here's the location of the drone. We give it a goal position that is outside the slide, somewhere here, let's say. And the drone is planning its path autonomously, trying to reach that goal. But when it starts off, it knows nothing about the scene. The best path is always the straight line, right? And since as it takes off, it starts to see that there are obstacles in the way, it replans its path on the go. And that's the cool thing about robotics, where everything has to come together in real time such that you can have some interactive performance, okay? So the path is constantly replanned along the way. Now, just to show you the kind of different layers of mapping that we're using. So we went from sparse mapping to denser mapping, and now I'm going to more semantically labeled mapping. And why would that be important? So if the goal, for example, is for this guy to reach that destination, maybe, the straight line path is not the best path to follow. Why? Because maybe there's places where there are humans and you want to avoid them. Maybe there's places that are going to affect the fidelity of your algorithms. For example, trees are not a good place to look for information because trees move, especially when there is wind. Or maybe you shouldn't be localizing yourself using cars by looking at cars, but buildings could be something that can help you better understand with high fidelity, estimate your location, your position. So giving a semantic information on these pixels, like what is a road, what is a tree, blah, 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 then you can really guide your autonomous path such that you can follow it with more fidelity. And let me give you one example. So here the goal is to fly your drone, your unmanned aerial vehicle, that's UAV, to land from wherever it's flying right now, identify a safe landing spot and land as soon as possible. In urban scenarios, meaning in a city environment. So we have sequence of images that comes in, like an RGB image. At the same time, you're running SLAM on the background that gives us 3D information about the world. We are densifying this map, but at the same time, we are processing the input images through a semantic segmentation neural network that gives us a semantic label for every pixel, like, I don't know, this is terrain, this is building, whatever. Don't remember the color coding. And then we train a reinforcement learning policy that maps such depth and semantic information directly into high-level commands for the controller, like move left, move right. And these commands then dictate where the UAV would be flying, okay? So expensive things like this can run on the cloud. And then, so that means that we cannot really run everything at runtime, but every now and again, to be able to receive information about where and how to fly next, depending on what weight you have given in each particular class on how useful it is for your navigation, how non-useful it is for your navigation. And here is one successful result. What you're looking at here is on the top left is the view from the drone. RGB image, red, green, blue. Then here you can see the semantic mask of the images that are being processed. And that's a drone, and it's identifying terrain, let me land. Of course, this comes after a lot of training examples, a lot of crashes in simulation, okay? That the drone has learned that, well, by example, by mistakes and by successes, what works well and what doesn't. But of course, I wanted to show you some of the failure cases as well to understand the limitations of something like this. So in this example, in a bit, the lamppost has no features on it, so it will not be detected in the SLAM map. So the safety pilot needs to take over because the drone is trying to land on top of it. And there's another example that the bushes get misclassified by the segmentation mask. They look very much like the terrain. So then that's another example where this method doesn't work very well. Right, now imagine that you have drones able to do high-fidelity SLAM and also scene representations, denser. How do we get them collaborating with each other? So here is a robotic agent that is running SLAM on board on its computer. So here are the poses of the robot, and here are the landmarks, and they're connected with direct constraints. You can imagine them like springs, and every spring is pulling and pushing in a different way, and that's when you let the network relax, come to a steady state, then that's your best solution to the problem, which is what we call bundle adjustment. And so you have one robotic agent that is doing that, and imagine that you have many robotic agents that they're doing their thing, they're running SLAM, right? Now, inevitably, after some point, this graph will become too big to be able to process in real time. So what we say, before you forget, because before you start overwriting information that has happened in the past, why don't you just send all that information down to a central server, down or up to the cloud, okay? So this central server keeps a copy of every map, right, to store all map data from all agents. And what can you do? Well, you can even do higher level tasks like place recognition to understand whether one drone's trajectory is overlapping with another drone's trajectory. So, these two maps, maybe you should join them, like what has happened here. So if this happens, then you need to run again one optimization run to be able to correct for any errors that have happened in the meantime. And then you need to inform any participating agents of these corrections that have happened. So here is the system in action. So these are 3 drones and a server. In this case, is a laptop. none of the drones are autonomous. They're all manually piloted, okay? So here you can see the views from the drones, and hopefully here you can see different point clouds. These are the maps that the server is storing. And we plan the path, or we guide the drones such that they experience overlap, such that these maps join, right? So what happens in the end, all of the drones work on the same map, and they exchange information. They're building a map of their environment collaboratively through the server, via the server. So best case scenario, you are able to collaborate with your teammates. Worst case scenario, there is no communication between each drone and the server. And then you still need to make sure that there is stability and you ensure the integrity of each robot. And that happens because every robot is able to run SLAM by themselves. Okay, so if collaboration happens, the cool thing is that at runtime, you have access to information more than your own. So that means that you can be more precise during your own state estimation. So let's say that one drone is experiencing a place that someone else has been to there before. It can query that portion of the map. Instead of building that map from scratch, it can actually localize off that map or even add more data to it. Follow-up, multi-agent collaboration. So obviously, this is a centralized system, so all data needs to pass through a server, and that's the obvious bottleneck. And for this reason, we are working towards more distributed collaboration. One thing that I'm really interested in, I'm going to show you this example, is this notion here, where you have a stereo camera, and every stereo camera, like ours, is optimized for a particular depth, right? Ours is optimized for our arm's length, right? So I'm not very good at estimating in centimeter precision things that are beyond the wall of the room, okay? And for this reason, having two different drones, each drone holding one camera, and if I can control this baseline, then I can have variable baseline stereo, if these two drones are talking to each other, that is optimized according to the depth of the scene. So how do we do that? Let me go a little bit deep now. So this is our work towards distributed variable baseline stereo. I'm going to talk about two drones for the moment, okay? So we have, as in all systems that you've seen so far, I have vision and inertial measurements. And in this case, I'm also adding ultra-wideband measurements that are giving us a sense of the distance between the two drones. We have raw data, images, relative distance estimations on the onboard estimator, and then these drones need to exchange information with each other, keyframe data, consensus variables. Okay, so let's look a little bit at what happens on this onboard state estimator. So we have the poses of agent A. So these are the keyframes or some intermediate poses, some representative poses of where agent A has been to. Trying my best here. I don't think I'm helping. Good. Then we have agent B that is also navigating, but they're experiencing common features and also experiencing different features. Yes, it's testing how well you are awake or not. So we have common features and we have features that are viewed by individual agents themselves. I don't think I helped the situation at all. So what we have on top of that is ultra-wideband estimates, right? That they come at a much faster rate. So these are these green arrows, these relative distance measurements. So here we go. I think I need to do this. Yes, and hope for the best. I hope that at least one of the two works. And so we use splines again to be able to interpolate using all of these data. And the question is, how can I optimize this graph when each agent has their own version? So this is going to be a real challenge because I'm going deeper, but I'll try and focus on the sound, okay? I'm not as descriptive, but... So imagine that you have a problem with 4 agents, different colors, okay? They're experiencing different features, some of them in common. Okay, so one way to optimize this graph would be using the reprojection error, the sum of the squared reprojection error of these features from the different viewpoints. Okay, that would be a way to minimize that. But now if you consider splitting this problem in 4, because you have these 4 agents, then common features are duplicated in this case. So this guy inherited this guy's feature. And so what would happen is that you'd have the minimization problem happening in each agent by themselves. So before I go there, if everyone is optimizing their own problem, they might come up with different solutions. So what we need to do is enforce some constraints, like the common points, like these ones, they need to correspond to the same measures, to the same locations, right? So we do that using some constraints here. And so what happens, so how can we do that to enforce that everybody, despite the fact that they're optimizing their own bucket of features, then some features inside my bucket are optimized by my neighbor, and he has his own bucket that he's estimated, but we somehow need to communicate between us what happens in my bucket and what happens in your bucket, okay? So we do this by using consensus variables, okay? So for every constraint, for every common feature, we introduce one dual variable. So what do we do? I say, in my bucket, I have one place where you're allowed to give me information about my feature. So I keep a copy of my own local estimate of that feature, and I also have that little box where you're allowed to tell me what my feature is according to your data. So I have 2 sources of information for that feature in my own problem. Okay, so what happens is that then when I'm minimizing this problem, I'm trying to minimize also the error between my own copy and what you say your solution is about that feature. And then I run my minimization problem, my own minimization problem, but I also take into account how I'm going to update the value of what I think that common feature is. I'm going to update that value according to what you say and what my minimization problem says. And then what needs to happen is that I need to also tell my neighbor in their own little box and tell them that's what I think the value of our common feature is. And this is based on, this paper here. It's using asynchronous ADMM for those of you who are deeper into it. But let's look at the video. This is the thing running in a simulation environment. So we have 2 drones. They have downward-looking cameras. So we are simulating everything. The view, the IMUs, the ultra-wideband. So in the simulation, we're inflating the size of the drones just for visual purposes. They're not actually crashing. And what's cool here is that these drones are controlling their baseline in order to maintain a constant, almost, level of error, of expected error, depending on the depth of the scene that they're looking at. So that's why they have downward-looking cameras, and they're looking at things that have a different morphology, okay, of the terrain. I have to say, well, that's recorded, but anyway, we tried to run this in reality, but we lost the drone. So this was too high up, like 30 meters up, and I think that's where our limit is with respect to the drones that we're using. Right, so with these 3 challenges that I bombarded you with information, what we are trying to do is that we are trying to teach robots to see and collaborate, so robotic perception and collaboration, because we believe that these skills are key to boosting robotic autonomy, to going towards the goals that I showed you right at the beginning of the talk. So the title of the talk is, Are We There Yet? So let's look a little bit at the timeline of robotic perception, vision-based robotic perception. I will not start from Adam and Eve. I will start from 2011, Fukushima disaster, okay? Fukushima disaster happened, and we had robots able to play the violin, but we didn't have robots able, or drones, able to go into the disaster site, so we had to send people in. And any robots that went in, they had to drag with them the Ethernet cable. I don't know if you've watched videos. It was painful. 2012, we showed that autonomous flights based on vision are possible. 2018, this highest impact journal in robotics called Science Robotics announces the 10 grand challenges in robotics, and among them is AI for robotics, swarm navigation, and visual perception in visually degraded environments. So inspired of that, inspired from these, many problems and many groups have been, well, many problems came up and many groups and many funding sources have trying to be working in this area. But continuing on the timeline, 2019, we showed the first collaborative monocular SLAM for a UAV swarm. And also Skydio releases this drone that you can buy off the shelf that I believe it is the market's most advanced AI system, okay? So maybe it's not the best platform, but it's the best software, the best automation that you can buy off the shelf, even today. 2021, DARPA has this grand challenge, subterranean grand challenge, where the idea is that a lot of money is given to large teams to come up with robotic teams that they're able to navigate through a network of caves. Caves. To be able to navigate through smoke and, in general, degraded environments to do some tasks. First of all, they will need to communicate, but also identify some key areas that they were given images of. But these robots have not been to these places before. Now, the winners were also my colleagues at ETH, so they were part of the team, and they didn't use any drones, although they had some drones in the earlier challenges. They didn't use any drones because they would not work well enough. So they used their walking robots. I don't know if you have seen Animal at all. So this is a quadruped robot, and in the end, they managed to navigate through these difficulties using haptic feedback, okay, from the caves, basically. So 1 month ago, so the timeline goes, 1 month ago, Skydio releases a new version, their drone, their X10, largely having a lot more capabilities as a drone, like being waterproof and having a thermal camera on there. And they also have flashlights to be able to navigate in the darkness. Now, it's a start, but it's still a bit shaky, okay? So I want to show you a little bit where it is, where we are going, where the community is going. And fast forward 1 month ago to today, where do we stand? Do we have a drone or a team of drones that is able to navigate autonomously and collaboratively take decisions on how to act in a challenging mission? So can we monitor a construction site using a team of drones? Can we monitor the wildfires that happened in Rhodos last summer? Well, no, okay? So this is where the idea of my ERC comes from. And I'm using my previous challenges to show you a little bit where we will be going within the next 5 years. So we now expand and think we need to look at different sensors, and I think we are very much aligned with where Skydio has gone to. So we need to be looking at not only vision, LiDAR, thermal, event-based, okay? So to be able to then say which sensor to trust and when, how to fuse all of that, then okay, what makes a useful scene representation? Point cloud is enough for navigation, but then if you really want to have your robot avoid obstacles while flying, you want a denser reconstruction. But if you also want to build some more intelligence of that, maybe you want to show it that this is a tree and this is a building, right? That you want to distinguish how you do this thing. So, but what is a useful scene representation? How can I query all of that information effectively, right? And then, of course, how do you bring all of that together when you think about the swarm? What information do I need to share with my neighbors? What is the minimum information that I need to share such that we can collaborate, right? What is this extra bit of information? that is going to be useful, such that we are able to collaborate as a team, right? And also importantly, when you are thinking about wildfires and all of this dynamicity in the scene, maybe the question is, where should I look for information that is stable enough that I can localize from, okay? And I did spend most of the talk showing you videos of drones because I use them as a platform of, they're very challenging platform. They move very fast. They can gain the overview of the scene. They can navigate through windows. But they're also small, and they create a nice, challenging setup for research. So we need a minimal sensor setup. But the idea is that if you are able to do that with a drone, to do all of that with a drone, then the extension to other types of platforms can be realized. So it's the same sensor setup that you have on the phone or you have on a VR set. And here are some example projects. So for example, we had a project with Swiss Railway that we've been trying to automate or estimate, basically, the navigation of the train with the outlook of automating it, okay? Using event cameras because, yes, you're navigating on 1D, but you're navigating very fast. And I wanted to show you one more video here with this guy, this autonomous excavator, just to show you that we can do more things, not just drones. So this is a big project. It's together with a lot of colleagues from mechanical engineering, so mechanical engineers, civil, architects, roboticists, that we came together to use this autonomous excavator. So we equipped it with lots of sensors, and the task was to scan the area for stones. We chose stones that are too big, like a ton each, such that we can show that you can do more things with robotics than you can do with humans in this case. And we said, let's try and build a wall. So the excavator is scanning the area, is figuring out the shape of the stones, and there's a physics simulator running in the background that it's thinking, which stone should I choose, and how should I place it such that the wall will be freestanding? And here it is, after a course of a few days. It's not very beautiful, but it's a wall. And I think it's a very good example where interdisciplinary research can make something like this possible. And of course, I wanted to also show you what robotic perception can do, which is, to me, is the glue that brings everything together to create something like this. And yes, that was it. Thank you very much for your attention. Yes, sure. If there are any questions, any question is a good question. Michalis.
Thanks very much, Margarita. Thanks very much, Margarita, for the great talk. I was thinking, while I was listening to your talk, I was thinking about something that I heard from the director of Boston Dynamics, which I think also points out how mammals think about the world, right? Mm-hmm. He says basically that their job became much easier when they started forecasting the state of the world in the next, let's say, few milliseconds or seconds. So in connection with the stuff that you showed on machine learning, and looking at the progress that machine learning is doing nowadays, for example, I've seen the segmentation models that you're using. I mean, probably with the developments in the last 2-3 months, you can probably run them on the drone, right? With the new, faster foundation models that are, maybe.
We're getting closer and closer, yeah.
Yeah, so I mean, with fast segment anything, let's say. So my question is, have you integrated this aspect in your work, like forecasting the state of the world a little bit in the future in order to inform, let's say, the decision-making process? Or do you think it makes sense?
I definitely think it makes sense. That's brilliant. So, not particularly, not in my work, because we typically assume that the world is static. It's largely static. So you explain basically what you are looking at, the motion that you see, you experience, you explain it as ego motion. So there is some prediction about how I think I will be moving and how I think the environment will be like, but it gets all the more interesting when you start modeling, and this has been done, how pedestrians will move, but I think that's even more interesting and challenging when you're thinking about things like fire. How would it move? And smoke, how can I stay away from smoke? Yes, I want to run robotic perception in visually degraded environments, but I'm not doing myself any favors if I focus just on smoke, right? So I need to, so these are very good.
And also for the body, right? So that you exploit the inertia of the drone in order to make something more efficient, let's say.
So in this case, yeah, so you mean in my path, so yes, haha. We have a work that we're trying to do that in the sense that we noticed that if you have very aggressive maneuvers, okay, it's not very intelligent, but it's true. We noticed that if you do very aggressive maneuvers like change your direction all the time, then you eat up your battery much faster. So we use the path planning algorithm more like handcrafted to say avoid the start-stoppy moves. I have to say that we're using small drones, but I think the more and more things you port on that, or if you're thinking of things like a train, then you definitely need to think about things like this. Very nice, thanks. Margarita.
Thank you, that was a fascinating talk. I've got several questions. My most important one is whether you could adapt those points that you are sensing based on patterns, for example, so you can better localize some important features, for example.
Yeah, so the question is, what kind of features are good to focus on in order to help you with the tracking? So this is a whole body of research. So I come from the handcrafted feature school, which says, I've seen gradient changes to work very well, so let's try and focus on areas that have high intensity changes, but also they're able to be repeatable with time and different viewpoints. But then there's this whole other class of methods that is learning based, and they are telling us, you know what, here are examples of things you can track and figure out what features will help you. And there are methods that do that very well, but also for specific cases, and methods that do that very well for specific cases. So there's a big research area that is trying to marry the two, like use geometry for what is good for and use learning for what is good for. For example, if you think about the place recognition example that I showed on re-recognizing a place, deep learning techniques are much, much better in dealing with seasonal changes than handcrafted techniques. But with viewpoint changes, we are much better with the handcrafted techniques. Now, if you want your system to re-recognize a place no matter what, if it's a seasonal change, if it's a viewpoint change, then that's where the beauty comes in, like all the research that has to happen.
Is there the freedom technically wise on the drones to change the directions where you point those the lazy LiDARs?
So to, again, can you repeat your question for me to understand?
From what I understand, you send the signal and it comes back, right?
So if you think about a laser, yes, you can consider that you send your signal and come back. Or you capture your image because the signal is from the light anyway, and you capture whatever that image is telling you. Yeah.
In the case that you send the signal, is there a freedom of changing dynamically how you send that signal? For example, the direction of the various beams, or localizing.
Nice.
This is what I was thinking.
Interesting. No, not yet at least, but that's an interesting area. So the most relevant thing that I can say is that because we usually work with vision and everything comes global shutter, everything comes at the same time, all the pixels, the equivalent that I can think of is this event-based sensing that is giving you information only in places where things move and change. So this is a case where it's telling you that's where you should look for something interesting is happening in these pixels, and you don't need to process the whole thing. But we are so behind, and it's so difficult to process these events that we're still, as a community, I mean, not just in my lab, we're doing baby steps.
Okay. Well, thanks for the talk. I thought it is very fascinating, but at the same time very scary to think that we're training these robots to do things that we do. And from this thought, I was wondering, in the 3 challenges you discussed, if we are using us as a benchmark or not. Because I can imagine, okay, for SLAM, we are doing pretty well. For visualization, we're doing pretty well. But for communication, I don't think we are the best beings
Yes.
in that.
Yeah, I guess maybe I'm guilty in the fact that I showed you the nature-inspired versions, like the videos in the beginning. And yes, I won't lie, the inspiration is what is it that we can do, but I think that in some of these challenges, already we are surpassed by what our algorithms are doing. Okay, so yeah, I'll give you one example and get back to your question. So we gave this task. We used to have these open lab days, and we're trying to do these interactive demos for the visitors. And we gave the task to people to look at a pair of images that may or may not come from the same place, look at them for 3 seconds, and then reply, are they from the same place or not? Okay? And of course, we tried to give the difficult ones. And then we were showing what our place recognition algorithm was able to do. And yeah, well, algorithms could do it in milliseconds, right? But after a lot of training data, and humans were also confused because, you know, you're looking at an image, it's like, I don't know, it's too dark, I can't see. So in some specific cases, we are already, if you'd like, oh my God, artificial intelligence is doing better than we do. So I agree with you, it is scary, right? We cannot stop it. Only thing we can do is, I think, talk about it, what's scary about it, and guide it, okay? So in my dream world, I want to have robots that do things that I'm bored to do, and they can be, produce, like keep the economy going, and I can be doing, I don't know, the things that I really, really like to do. And I don't want to be, I don't know, scanning my items at the counter, for example. I'm just saying. So I don't know if that's where we're going, but I don't think that being scared is, yeah, it's a reason to step back, right? And I usually give this example of there's a knife in the hands of criminal, it can do harm. In the hands of the surgeon, it can save lives. So it's a tool. You decide how you use it. So, but yeah, a whole discussion about ethics and AI and where we're going with this. I think, yes.
Hello, Margarita. Thank you for this talk. I would like to ask you, in the case of localization and fusing several information together, do you use standard algorithms like complementary filter or Kalman filterings, or you invent your own in your research?
We invent and we copy. We adopt. So I think the SLAM community has been going largely towards optimization techniques that this performs much, much better than any kind of filtering approach, in the sense that you can process a lot more data for what it is that you get out of it. So optimization techniques work better. But then there was a paper that showed that despite that, you know, the fact that it is that you're gaining with filtering is that if you're missing information, then you constantly have a measure of your uncertainty, right? Which is something you don't get at an instant with optimization techniques, and that you're able to have that at an instant, for example. So the answer is that typically we use optimization, but everything is fluid and is subject to change. Yeah. Yes.
So yeah, thanks for the talk. What I was wondering is that given that every environment we saw was pretty sterilized, I think that semantics may play a huge role in this, learning semantics given a scene. And I was wondering whether you could do something like use inverse reinforcement learning from an expert in order to learn a policy that, given a semantic segmentation map of a scene that is constantly evolving, so that maybe that it could map a segmentation map to a certain behavior. So let's say that in this image we see a pedestrian. How does the expert act?
So, did I get this right? You're talking about a system where I don't need to explicitly tell it what happens in between, but make mappings between labels of pixels and success or failure with respect to what it is that you've done.
Yes.
Yes. Yeah, I think that's one way of, yeah, I don't know, I think it will work. Whether it will be the end solution, I think not, but that's just my gut feeling. I think that we need to somehow guide the process a little bit more, thinking also with respect to the landscape of semantic algorithms that we have out there today, that they're also uncertain, right? So they're far from perfect. They're also difficult to run in real time yet as well. And with semantics, you open a whole new thing, right? To what level do you add a semantic label? You know, there's all this discretization, quantization of information that is happening. Yeah, so I think it would be an interesting thing to try. Maybe people have tried already, I don't know. But I think there's the rest of the things need to play a role in it as well. Yes? No? I don't know, yeah? Panayota, there's one more here. And you guys tell me when we need to stop it. I don't want to, yeah.
Yes, one more question about the swarming dynamics. I got this idea from I work with molecular dynamics, where you simulate millions of particles, and there you've got the notion of coarse graining, where you group those agents. In our case, it could be atoms. In your case, it would be the drones, for example. Is there this notion in terms of scaling up the work of this swarming control, where you could have high resolution around in the neighborhood of each drone, and then you have a coarser image for those that are far away, if that makes any sense?
So I would translate it into having better granularity of your information in your immediate surroundings, and you don't really care that much about what happens. Yes, definitely. I mean, that's exactly the idea of decentralizing the whole problem. So when you decentralize your estimates, it means that you no longer have this single global godly entity that is called the server or the cloud that holds all of your map. So when I say display my map, I'm not going to be able to have it in a split second. But what will happen is that I will have a portion of the map, you will have a portion of the map, you will have a portion of your map, and then we can unfold all that information when we all talk to each other. So we need to, I don't know, do a two-step, like a broadcast and receive information to be able to understand the global map. But it's true. I think in robotics, you don't necessarily need, in swarm robotics, you don't necessarily need the whole map all of the time. It would be nice because it's easier for us to understand what every drone is doing, what every agent is doing. But yes, you need to cut down on the information that you process. I don't know, there is, but okay, whatever. Okay. Christo.
Try without the microphone.
No. Yes, it takes longer.
Thanks for the nice talk. Just a question from my side regarding the point cloud. Have you ever tried to create the point cloud on the drone and then use it for localization?
So what do you mean create a point cloud on the drone and use it for localization?
I mean on board the drone and not on a ground-based system.
Yes, absolutely. Every drone is building their own point cloud because every drone needs to be able to be autonomous, at least within this short period of time. It can forget things that happened in the past, but this is what we're trying to ensure, that you are able to process incoming information in real time and not wait for someone to tell you what the map looks like. So all the flight critical tasks are running on the drone. Anything, or that's the goal. Anything that is about beautifying the map, densifying the map, that they don't have to do necessarily with the absolute, flight critical, whether you're going to bump into an obstacle or not. All this has to run on the drone, because I agree, you cannot really rely on a good information from others.
Okay.
Good.
Thank you.
Thank you very much. Thank you, everybody.
Thank you very much. I failed to say in the beginning that Margarita has been included in a list of 25 women in robotics that you must know about. So even the most ignorant of us now know something about her. Thank you very much. Let me just announce that we will not have a colloquium in 2 weeks' time because there was a cancellation. The next one will be on the 30th of November. We will be hosting Professor Ioannis Emiris from the University of Athens and director of the Athena Research Center in Athens. So we are waiting for you by that time. Thank you very much again.